So we've already talked about the idea of conducting heat, radiating heat, convection, the wind, um, the movement of heat, all of these issues. But they really have been about the relationship to the human body and thermal comfort. Now we're going to just abstract that a little more and just look at just basically the motion of heat and energy, the natural processes. So we have conduction, radiation, convection, and the final one, infiltration. And what's kind of interesting in the process of most of the calculations we do on building heating loads, we only deal with this idea of conduction, the amount of heat that moves through our wall surfaces, which is measured in R value. We'll cover that in another lecture, what R value actually means. Um, but before we get started with that, reviewing all of these, I wanted to take the first minute and introduce this idea of BTU, which is a British thermal unit. It is the quantity that we talk about when we talk about the movement of heat or the creation of heat. It is a very well-defined quantity. 1 BTU of heat is the amount of energy that is required to raise 1 pound of water 1 degree Fahrenheit. And you'll see BTUs mentioned when we're talking about both heating and cooling. So we can have BTUs of cooling and BTUs of heat. It's just the quantity of heat that's either being added and or removed from an object and or an interior environment. So back to these ideas of our mechanisms of heat transfer. Radiation is important to us as architects because we deal with daylighting and sunlight and radiant heat sources, but also we embed radiant heat sources in our buildings when we create warm floor surfaces and fireplaces and other things that emit what's called radiant heat. Radiant heat is a form of radiation, just like daylight, but it is in another spectrum so that your eye does not see it. But it is a high energy source that creates, once it strikes a surface and is re-emitted, creates a heating of the surface that it strikes. And the neat thing about radiation is that it can travel long distances without losing its potency, so to speak. Just like light can travel, a beam of light from a flashlight can travel a great distance before it strikes a surface. Radiation's the same effect, the same kind of spectrum of energy. So it can be transferred from the sun 93 million miles to the Earth and still have not lost any of that radiant energy to space. And the same thing with a campfire, fireplace, or a warm surface in a building. It can travel a great distance, and the only time you experience the heat from that radiation is once it strikes a surface. And in that case, for thermal comfort, it's when it strikes the person in the room. So with that idea of radiation, there's radiation we want to control. Sometimes we want to absorb that radiation, and sometimes we want to reflect it away. So this graphic kind of describes that idea of where sunlight radiation can have a negative effect. So we have sunlight striking a dark roof. It's absorbing the heat, raising the temperature of the roof surface, requiring us to air condition. We could have a white roof that reflects a lot of the sunlight, keeps the temperature of the building down. So in this case, we are rejecting or trying to dismiss as much of the radiant heat that's available to us. So this can be applied to many different kinds of surfaces, whether it be lawns, blacktop, the color of surfaces, all affect how much radiant heat gets absorbed from it. And when we talk about that, we generally look at black surfaces being highly emissive or absorptive, and white being conversely lowly emissive and um, uh, very good, or excuse me, very poor as absorptions. Sorry, I'm kind of screwing that up a little bit. Um, but anyway, so with that in mind, there's this idea of roofing materials, the choice of roofing materials, the idea of surfaces that are shiny and reflective, reflect a lot of heat, rough surfaces, dark surfaces, matte surfaces absorb a lot of heat. So we want to keep that in mind when we're designing roof systems and landscaping systems and parking lots. For instance, a parking lot could be all blacktop or it could be permeable pavers with some grass growing between it. And all of that would change the absorptivity of the surface and affect the heat that's generated in that localized area. So one of the other effects that we're familiar with and we need to deal with as architects is this idea of transmissivity to radiant light. Once again, this is the light that comes from the sun, radiation. And when it is easily transferred through the glass without warming the glass significantly. And when it hits an opaque surface on the inside of a greenhouse and is reflected back off, it comes off and it goes in as shortwave thermal radiation and comes off as long wave heat radiation, and it can't get through the glass. And that's what's called the greenhouse effect. And the same thing happens on Earth with the idea of carbon dioxide in the atmosphere working as a kind of glass shield over the Earth, allowing the sun to penetrate it, but then blocking it when it comes back as thermal heat off of reflected surfaces. So keep this idea in mind about radiation. And many times with glazing systems, like not with greenhouses specifically, but with windows, we try in many cases to reflect the heat from the sun because in many climates, the glazing systems add more heat to the building than is really desirable. Another concept of the motion of heat and transfer of it is convection. And in this case, when we warm air, air gets lighter and moves higher. It becomes more buoyant. As it cools, it becomes denser and falls down. This creates a sense of a flow, a motion of air, and that motion of air can either be beneficial and or negative. In the case of a wall, without any insulation in it, if the air can freely move up and down like that, it becomes a pathway to intensify the transfer of energy through it. So it can be a negative thing. And one of the purposes of insulation is to stop that convective loop, that changing, that movement of air. In the inside interior environment, it can both create draft and it also can create thermal comfort. In the case of radiators, many times they're placed in front of windows and they use the idea of heating the air to create um, a thermal blanket across the surface of the window and it cools slightly and comes back down into the center of the room. So we use that convection in some cases in rooms to help distribute the heat in the room. Conduction is the one form of heat transfer that we deal with the most significantly when we measure heat loss in buildings or heat gain in buildings. And that's the idea of the direct transfer of the contact of one surface to another and moving heat. So in this graphic, we have the idea of a metal bar being heated. So it's very hot at this end and the heat moves through conduction to the metal surface, gradually giving up heat to the atmosphere until it cools down at the interior. So conduction, like I said, it's our main mechanism of calculating heat loss in buildings. And you can see here from this graphic a little idea of where all of the heat loss comes through in buildings. And this is a little misleading. It says walls have 35% of the heat loss and windows only have 10%. But that is not because windows are more efficient, it's just that there are less windows. And roofs have a large surface area, so they attribute to a lot of heat loss, and they're therefore one of the places that we like to create the most amount of insulation in our building. So I'll end that clip now, and we'll pick up on the next one.